Let's now go to the last part of the lecture and discuss some principles of data analysis. Let's look at the overflow, how data analysis is, the overview of how data analysis is carried out at Collider experiments and elsewhere. First, to start with, one needs simulation software that covers all detector cell, the readout electronics, and the object reconstruction. It is really the first thing to fully carry out the analysis in using only simulated events without data. This preliminary simulation that can amount to 1 billion up to 10 billion of events at a cost of about 4 minutes or so per event is a considerable factor in the total cost of the LHC experiments. So simulation software and the actual simulation are the first two steps. After step 2, one does have a set of simulated physics processes that can be used to obtain a design of the analysis. One needs to define a workflow of the calibration and a design of the measurement that should be carried out. In other words, if objects like muons or the Z boson or jets are to be used, it must be clear from the start what the calibration workflow actually is and what uncertainty in the calibration can be expected. Note that until step 3, there is no involvement of any real data event whatsoever. Then data taking can happen, and it happens with how you think the detector is located in space, what its resolution and its properties, including dead cells, are, and real data is recorded. This is little more than selecting events during the data taking, which is the trigger mechanism, and recording the digitization of the hits in the individual detector cells. So nothing much has happened. Data taking must use an alignment of the detector. So you do have to insert the locations of the pixel and the strips to be able to take prompt reconstruction data. Now, it cannot stop there because the actual alignment of the detector has to be measured with the real data. The large LHC detectors contract when ramping the magnetic field by between 10 and 15 centimeters. Because they are fully composed of steel and metal, this is really a substantial deformation that must be measured in situ. It is before the magnetic field is fully ramped, not clear exactly in which locations the detector cells end up. And therefore, in step 5, one uses the actual data to calibrate the detector. That is a bit, maybe that looks a bit dry. However, it's an interesting thing to do. We started to calibrate the timing of the detector, for example, by shooting bunches at the collimator. The LHC beam is the LHC beam enters the experimental cavern through collimators, which can be shut. And if low intensity punch is shot at the collimator, the whole detector is traversed by shells of particles moving at the speed of light. And from that information, one can obtain a relative timing of the detector. That's the first calibration that can be done. And it's an important one because each detector cell is subject to light guides, for example, of varying length, or cables transporting electrical signals that can only go with the speed of light, and all these cables have different length. And so cell by cell detector timing calibration is foreseen, and it can happen with the help of such beam splash collisions. Now, once the beam goes through the detector and collisions happen, one can perform a relative alignment, for example, of the tracking detector cells by injecting in the track fit a hypothesis that reflects our best understanding of the radiation pattern of charged particles. And from the geometric relations between the strips, for example, a strip cannot move in the direction of in the direction of the plane of the sensor, but it can move a little bit orthogonal to it. And by running many of such track fits, it is possible to extract the three-dimensional locations of the pixel and the strips relative to the beam spot where the proton beams collide. So now we are at step 5, a calibrated detector. It's been calibrated with real data. The data must now be reconstructed, and the simulation that we obtained in step 1 must also be reconstructed, because in these steps an ideal detector was assumed. And in step 5, the alignment and the calibration of a real detector were obtained. It's important that the calibration does not depend crucially on signal regions that are to be used later on. A good example is the Z boson. The mass of the Z boson and many of its properties were measured with high accuracy at the lab experiments, and the Z boson mass of 91.2 GeV is known to high precision, and therefore the momenta of muons can be calibrated such that the mass of the Z boson is correctly reproduced by the event reconstruction. Now, once you've done that, you have injected the Z boson mass. You can no longer measure it. That's fine as long as, so that's an example of a theory parameter entering the reconstruction. Of course, once you entered it, you can no longer take it out because you have injected it there. That's fine if the quantity is well known and you have no doubts about it. In other cases, it is less clear. Jet energy calibration for very high momentum is one example where we have a few events to calibrate high PT, highly energetic jets as a function of other jets that may be in the event. But these events are so rare, and there are signals beyond the standard model that may spoil the simple relations that we put in, such that physics beyond the standard model may be absorbed by various mechanisms in our calibration procedures. Usually it's not a very important point that such a thing happens, but it has to be kept in mind. We're doing an experiment here. An experiment must be calibrated. whatever enters the calibration procedure is an assumption in all the subsequent measurements. It's an assumption and not something that's actually that you can gather information on by looking at data events. There are teams in all large collaborations working on the reconstruction and the calibration. Therefore, each analyzer, each participant at most takes part in a very small subset of such tasks. What everybody has to do, however, is to estimate the systematic uncertainties, for example, based on data control regions. We had one example was the C boson mass as a proxy, as a calibration tool for the momenta of the muons. If we carry out an analysis with muons in events with, let's say, more jet activity, then we can redo this calibration procedure and check how well it works in the event sample that is under study. The amount of misreconstruction of the C boson mass could then, in principle, in some example, well, as an example, be used to estimate the systematic uncertainty on the muon momentum reconstruction. Once the systematic uncertainties have been obtained, the time of the mode of operation changes. Up until 0.7, we were in the regime where the analysis was optimized. You would try to select events based on optimal sensitivity of the parameters that you're interested in. It can be a cross-section of a rare process, it can be a search for a SUSE signal, whatever. At a certain time, you freeze the analysis, which defines what kind of measurement you are doing. In a statistical sense, you define the estimator. That means you freeze, you can no longer touch the definition of the analysis. And then you unblind, which means you look at the data in the signal regions. It's the first time that you look, and in many analyses, it's a crucial step. It's not something you decide on your own. It follows presentations that you give to your colleagues, and a common consensus, is reached that the way you estimate your uncertainties, the analysis design are good enough to move forward, so you can look at the data. So you unblind, and essentially you have a result. With the result, you perform a comparison, for example, of your data that you have measured, that you have seen in your signal region, and you compare that to the estimation of your background. The estimation of a background can be obtained in various ways. It can be taken from simulation, and we will now discuss other means of obtaining background estimation. So step 9 is simply looking at the results and comparing data and simulation. It goes together with the last step, which is to cast the result in p-value or in a probabilistic setting, obtain, for example, a limit on the production cross-section of a new process that you're searching for, supersymmetry, a C prime boson, whatever, or a measurement of a standard model quantity that you're interested in, like the top mass, like maybe hopefully soon the W mass, and similar things. You obtain the result of your measurement as a function of the uncertainties on your background estimation and all the other effects that you have accounting for before you froze the data, and then you publish the result. There are a few things that you absolutely cannot do, And one of the things that you absolutely cannot do is change the question after you have received your answer. This is no longer physics. If you make an analysis, ask a specific question, the question could be, are there events that are reminiscent of a supersymmetric signal? That's what I used to work on earlier. And then you unblind and the answer is no, there are no extra events. And then you look at the data and you find in the data features that look like a different signal, not the one you were looking for, but maybe like a different one. And you change your signal regions such that the events that look a little bit different than the standard model, that they are grouped in one box and the other box that stays empty. And you look at that particular box and maybe you even compare with a new signal. Then the p-value that you get has no meaningful interpretation anymore. It's not science. Science consists of well-formulated hypothesis tests. If you violate the principle of a blind analysis in one way or the other, if you really grossly violate it, one can correct errors. If you have a bug in the code, it can be corrected. But if you start changing the definition of your search, of your hypothesis, eventually we make tests. We test the hypothesis of the standard model against alternative hypotheses, and we do so by comparing the likelihoods to observe the data under these various hypotheses with each other. If we change the hypothesis, the p-value has no interpretation anymore. I insist on this point because it is sometimes violated, and in these cases, the work is useless. Now, with that caveat in mind, let's look at the different steps. How we compare data with the prediction. As I said, before the data is analyzed, the physics question must be formed. The hypothesis tests, the structure of the hypothesis tests may look like, is the standard model true, or is it rather a specific model beyond the standard model that's true? If you look at any or most of the diagrams that compare data and simulation in any of the publications in particle physics, you will find data. Data has error bars. The error bars are statistical. I did not put units here because this is a schematic example. The errors are either it's written in the caption what the errors are. By default, they are statistical. In other words, they should roughly be of the order of the square root of the number of events in that bin. Then one has some sort of prediction. The thick black line indicates the null hypothesis. For example, the standard model prediction is a typical null hypothesis on top of some backgrounds. So maybe this black line is the process of interest. I don't know, what could be anything, a Higgs, top quarks or whatever. There's a kinematical variable here, maybe a spectrum of transverse momentum spectrum of a particle. It can be a mass, and then you see a bump, whatever. I do not specify it here. So there's an interesting process whose null hypothesis you look at. There are backgrounds I show in color here that are processes that enter the selection by various reasons and must be estimated, but are not the target of the analysis. And then there is maybe, that need not be the case, but it can be, there's an alternative prediction according to beyond the standard model hypothesis. So many of the tests of the standard model are formulated in this way. We estimate our backgrounds, we consider a signal process that is interesting, and we obtain a prediction of the interesting process. under the standard model assumption and beyond the standard model assumption. And that leads to this structure. How can the predictions be obtained? The prediction, of course, is something that's compared to the actual measurement. So the prediction must be obtained from somewhere else. Otherwise, it's not a comparison. The simplest thing to do is to fully simulate the detector, the collision process, the pileup, the response of the detector, the event reconstruction, and the different steps in the analysis chain, and to thus obtain a number of simulated events. That's a standard technique that's done in almost all the cases. Almost all analyses are carried out fully on simulated events. The simulation principle, the simulation technique is called Monte Carlo. It is a form of integration that was devised first in a meeting that was held in Monte Carlo in the 60s. So we call this the Monte Carlo events or simulated events. Just if you heard a jargon, if somebody tells you, look at the Monte Carlo, he's telling you, you should disregard the data and test your analysis in a fully simulated setting first. One can use other data regions. We call these control regions. These are different from the signal regions where we look at our signal. One can look at control regions that have the same prediction, or where the prediction for the backgrounds or for other aspects is in close relation to the signal region. A good example is the branching ratio of the heavy massive bosons, the W and the C boson, to muon and to electrons is roughly the same. If you therefore have a background that comes from, if you have a signal region that's dominated by electrons, and you want to study the rate of a specific standard model process that is not so well known, you can look at the same process in the muon channel. And because the muon channel is not a signal region for you, it is fine to do so. And you can look at this, you can look at the muon control region without looking at the electron signal region, assess the level of background there, do your studies in the muon channel, and gain confidence in the quality of your reconstruction, in the quality of your background estimation. One can measure the rate of muon events, for example, and multiply with a translation factor to obtain a prediction for the electron channel. For example, it is known that ballpark muons are reconstructed with a 95% efficiency. Electrons, let's say, are reconstructed with a 70 or so % efficiency. Now you have two of these guys. 95% squared is roughly 90% for a dimuon system. Electron efficiency squared is, what did I say, 70%. So it's 49% for the dielectron, sample. And if you now want to translate your control region measurement in the muon channel to the electron channel, you have to multiply, you have to divide by the 90%, that's the muon reconstruction, and multiply with the 49%. So you multiply with a factor of 0.49 divided by 0.9, and that's a simple way of getting a background estimation in the electron channel from a muon channel. Of course, whenever you use such translation factors, you're making assumptions. The assumption being that the process you're looking at in the muon and the electron channel are indeed from the same origin, and that the branching ratios are the same. Now, the branching ratios of the C bosons to muons have been measured at, and to electrons have been measured at lab, and we can trust them. But what we can maybe not really trust is, depends on the analysis, but it can be that the background composition is very different in the muon and the electron channel. And if it's different in the muon channel and it's wrong in the muon channel, then you get a wrong answer by simply multiplying that. you see that this is where the work goes, because you want a background estimation for a signal region, you get to look at your control region, and now you need to understand what's going on in your control region. And in principle, this never stops. One can refine an analysis until the end of the days. At some point, one has to stop and say, okay, there are subleading effects that I ignore now. I know they are smaller than 5%, and I quote this as an extra uncertainty. So predictions can be obtained from simulated events, from data regions with corrections, and sometimes also from theoretical calculations. Sometimes it is possible to compute the number of expected events by running a computer program which performs a complicated quantum mechanical calculation. All three paradigms are used simultaneously. All of them have very different systematic uncertainties. In a realistic analysis, each one appears at some point, at some step, has some use. Often an analysis, a data analysis, a specific hypothesis, for a specific hypothesis test, there is a central idea that's related to the leading systematic. That is to say, if we look back at our statistical and systematical uncertainties, for each of our measurements, if you carry them out, you get an idea what is limiting here, what are the one or the two leading systematic uncertainties, maybe the lepton identification, maybe the accuracy of the calibration of jets, and then one can make the analysis design such that this specific, your leading systematic uncertainty is improved on, plays a smaller role. And that interplay of understanding your systematics, designing the analysis such that it has a small impact, while all the time not looking at your signal region, only look at the control regions that are not populated by your data. That's where the bulk of the work goes. So after the analysis is frozen and the predictions are obtained and the uncertainties have been obtained, the data and the prediction are compared. Here's an example, a simple example of what this can look like. This example is from mostly simulation-based estimation. It is for Z bosons to the dimuon channel, something that we understand very well. As I said before, here's the Z peak around 90. The position of the Z peak is typically not a quantity we measure because we use it for the calibration. However, there are dimuon events with a higher invariant mass. The spectrum falls very quickly up to 2 TeV, where where we have where the distribution dies out, and the precise shape of these dimuon events has significance for studies beyond the standard model. For example, you may look at the cousin of the Z particle, something that may exist but has not been found, a so-called Z prime. There would be a particle that also decays to leptons at a certain mass. So one would expect to see a small peak at somewhere in this distribution. That would be indicative of a new heavy cousin of the Z boson decaying to muons. And the spectrum here can be interpreted in this respect. Of course, you need to be very careful. You have a little bit of a structure here. Is this statistically significant? There's a little peak here if you look closely. To understand that this fluctuation is purely statistical, requires you to fully understand the systematic uncertainties of all aspects of the reconstruction. In particular, as is done here, if we directly compare data and simulation, it means that every miscalibration of the real detector, every lack of theoretical understanding directly affects the result. If there is a contribution to missing in the theoretical calculation that's relevant at high energies, it may very well be that your prediction is consistently below the data and your data is above, and you may say, oh, something is wrong with the standard model. But in fact, the only thing that's wrong is with your calculation that entered your simulation, which therefore has to be carefully scrutinized in terms of systematics. So you need you always need a complete assessment of all the effects that you neglect. In this example, one would typically not interpret this as a direct, one would not directly compare data and simulation. One usually does that if the backgrounds are known to be extremely small. That can happen in the tails here. Let's look at the 2 TeV dimuon invariant mass, and you can imagine searching for events further out. The background prediction under the standard model hypothesis is tiny there. You could go to a regime where you expect less than 0.1 events. So that just means your Poissonian mean of your background expectation is 0.1. In other words, it takes on average 10 repetitions of the same event, of the same experiment until you observe a single event. So 0.1 event background estimation is a small number, and you don't care if your uncertainty is large. So even if you have an imperfect calculation that gives you a 20% uncertainty on your simulation-based background expectation, you will get 0.1 plus minus 20% on that. That would be 0.02. So two small numbers, and it doesn't matter because let's say the signal you expect is 10 events. So you have a tiny background and a large signal. If the background is tiny, you can tolerate large uncertainties, and you can then without a problem estimate these purely from simulation without just running the computer simulation and not too much work. If there is a main source of a large uncertainty, let's say the jet energy calibration, or let's take the example here, it's probably the best example, that can be derived from this plot. Let's say the muon momentum scale. If the main source of an uncertainty is known, the comparison can be reversed and the measurement can be turned into a calibration. The example here shows the C peak at 91.2 GeV. I brought the example before. It is used to calibrate the muon reconstruction. So it's not an achievement that for these two bins here, data and simulation, agree so perfectly. This is by construction. We adjusted the muon reconstruction such that this comes out, reducing the uncertainty from the alignment of the muon system, for example. Once the muons are calibrated, we can use these events to calibrate a recoiling jet. Let me sketch that for you. Yep. Let me sketch that for you. If what are these events? These are Drell-Yan events. So wait, does this work? Pen. Okay. No, it doesn't work. Okay, it doesn't matter. I can explain it. It would only have been a small sketch. Once we have a well reconstructed and calibrated C boson, we can exploit the transverse momentum sum of the detector, which is supposed to, of the particles in the detector, which is supposed to be 0. The protons, the initial protons don't move in the transverse plane, and hence the transverse momentum adds up to 0. That means if there is a jet on the other side of the Z boson, we know that the momentum of the Z boson and the momentum of the jet must agree. Because we've just measured the momentum of the Z boson with high precision, because we calibrated it on the Z peak, we can now also use that information to calibrate the recoiling jet. That's exactly how jets are calibrated. There's a longer story to it, but that's how it works. We use so-called standard model candles, and the Z boson is the most famous standard model candle. We know most of it, and we calibrate whatever we observe in the detector to it, because we are sure that we accurately describe it. Of course, we lose the Z boson measurement as an observable, the Z mass measurement as an observable. Once it's used for calibration, it's what is coming out. Good. There was a simulation-based estimation. Now let's go to the exact opposite. Let's forget about simulation. Let's only look at data. Let's say we have two variables that are uncorrelated. In this case, it is the impact parameter resolution and the isolation of a lepton. We have the, it's the impact parameter significance. The x-axis tells you, how far, essentially is a measure of how far, how small a particle's track approaches the primary vertex. So the points to the right, the gray dots to the right, amount to a lepton that's going a large distance. So it may come from heavy flavor decay, so a BTEC jet, for example. The relative isolation is the amount of extra activity in the vicinity. So we have two variables here that discriminate a lepton from a B jet. A B jet hadronizes into a B meson. A B meson can decay to a muon. If there is little extra activity around, you can actually mistake a lepton for a B jet. And that's a big mistake, because a lepton is a probe of the W boson and the Z boson, while a B jet is a hadronic source. However, sometimes in the detector that can happen. Signal leptons will have a small impact significance if they are promptly produced, and will have a low relative isolation because there is no hadronic activity around. Background events will be in one of these regions with high values, so either a high impact parameter or they are not isolated, there are other particles around, high values of the isolation. Now, if you can prove otherwise or from first principles that the two variables are uncorrelated, then you know that A over B equals C over D. If these two measurements have nothing to do with each other, that is, the relative isolation and the distance of closest approach to the beam spot or the interaction vertex, then it holds that the number of events in these regions, A, B, C, and D, that you can suitably define, satisfy the relation A over B equals C over D. If this is so, and your signal sits in the region C, then you can obtain a background prediction, an estimation, so C estimate, by exploiting this relation. And you rewrite the estimation of the signal is the observation in D times the ratio of the observations of A over B. Here, no simulation enters whatsoever. These are only properties that you observe in the real detector. However, assumptions do enter. Of course, you have to know from somewhere that these variables are suitably uncorrelated. You have to know that this relation holds. The data will not tell you because you're using the data to obtain an estimation for the background in the region C, but you also suspect your signal here. So you cannot use these 4 numbers to check the relation. You use these 4 numbers to obtain a prediction. So there are assumptions entering here, but that's a procedure that's highly data-driven. Here we have almost no dependence on the simulation. Okay, that is one example. A disadvantage of this method is that this simple formula only holds for rectangular cuts, and you cannot, for example, the events in maybe there's a problematic region here, then you have to open a gap and you cannot change the definition. You cannot move the region B closer to A while not moving the region D closer to C, because otherwise this relation is violated. We call this the ABCD method. It has advantages and disadvantages, and the restriction of rectangular cuts makes that is one of the shortcomings. A generalization of this ABCD method are translation factors. Sometimes ratios of yields are more stable than the yields because systematic uncertainties cancel. A good example is the branching rate is a process that decays via a process that produces a Z boson, for example. You know very accurately that the Z boson, how the Z boson branches into electron and muon final states, and this can be exploited in various ways. As I said before, you can measure a yield of your background process in a muon control region and use the ratio of electron to muon from the simulation to obtain a background prediction. It's exactly what we're discussing now is exactly parallel to the example we had before. Look at the structure. You have an observation in a control region, and you multiply this with a translation factor that's obtained from MC Monte Carlo from simulation. So you don't fully trust your simulation. You do not trust the normalization of your simulation, how much it predicts, but you do trust that you get the ratio right between the signal and the control region. So there are various degrees of trust in simulation that can be used to obtain a background prediction. Sometimes, as in the example of the Z boson decaying to electron and muon, that's really the way forward. In the example, when we exploit the Z branching electrons and muons, the ratio is known to very high precision per mil level, but the normalization may not be known at all, and we can measure it in a sideband that's free of a hypothetical signal. I put some example here from a SUSY paper that uses highly energetic, that uses signal regions with that are sensitive to processes with supersymmetry, with spectacular events that are difficult to simulate and difficult to calibrate. And just to highlight what a typical analysis result may look like, here the prediction is a product of several translation factors. It is shown in green. And after we were convinced that the background estimation is actually correct, we unblinded and put the data measurements on top, and you see that the data-driven background estimation in green and the measurement agrees within uncertainty in all the bins. Okay. Another interesting procedure that's used in Z and Higgs analysis is the sideband subtraction. If the shape of the background is known, then it can be subtracted. So here that's an example of a Higgs boson decaying to two photons. That's the the first Atlas 13 TeV measurement from Atlas for a change. You see that there is a small wiggle. That is the Higgs boson signal on a large background of diphoton events that are rather difficult to simulate. Now, what is done here is the shape of the background is fit in the sideband such that this blue dashed background prediction is obtained under the Higgs boson mass peak, and then it is subtracted from the data, and the result of the subtraction is shown below in the pad, where an impressive peak is recovered after the background estimation. So the fit is in this case obtained from a functional parametrization. Now, a functional parametrization, there are polynomials used, and there are other vaguely motivated analytical functions used in these fits. And in principle, I mean, you do not know what is the correct function. So one has to try different functions, and these different functions with the different parametrization, of course, amount to a systematic uncertainty. And it's even a difficult one that leads to a lot of discussion, because what is, at what point have you covered all, at one point can you be sure that the uncertainty that you put into your parametrization really covers this? A fifth order polynomial, a seventh order polynomial, a polynomial multiplied with a logarithm or with an exponential. Or some more complicated shapes that has some physics motivation. This, of course, is ambiguous, and this ambiguity is reflected in a systematic uncertainty on this prediction. That's, by the way, not shown here. One can also take a simulated background. That happens in the example below. You have a background template, the blue shape here. The blue shape comes from simulation. You just run your events. You do not, what you trust is the shape. You trust that it raises here, it's flat under the signal peak, and it continues and falls a little bit, so that you trust. And then you fit this to the data in a sideband that could be between, that could be below 60 or above 120. And you normalize it. So you do trust the simulation of the shape of your background, but you do not trust the simulation of the normalization, how much you get. In this way, you obtain a prediction that is essentially the ratio of the integral of your background template from under the peak to outside the peak, and that multiplied with the yield that you measure in your sideband. So again, by trusting different aspects of the simulation, different background estimation techniques can be devised. I repeat, so here we trust the template, we adjust it that it matches the normalization in this normalization region here, and we use it to predict that in each bin here we have roughly 100 background events. And we can then subtract that from the data measurement, that's all the black dots, to obtain a measurement of that is shown as the little black crosses here. So that's the background subtracted data measurement. Okay. The next concept, the so-called tag and probe method. How do you know that a muon candidate that has been reconstructed in the detector really is a muon? Can it not be something else? And what is the rate that it is something else? And what is the rate that it has been, and that it has been, that a muon candidate that was, that originates from a particle of interest, like Z boson, Higgs boson, or something, is really reconstructed. Recall the definition of efficiency, or keep it in mind. The definition of efficiency is the following: the probability that an existing object is reconstructed accordingly. That means if you know that a thing, an object has been created, the probability that it's really reconstructed and identified, that is the efficiency. An inefficiency is in statistics called a type 1 error. A different mistake is a misidentification. If you have an object reconstructed and you ask the probability that this object reconstruction and identification is actually correct, that does not ask for the efficiency, that asks for the purity. That if the question is different, the question then is, I have a set of candidates. What is the efficiency that these candidates are reconstructed correctly? Definition of efficiency starts with true events and asks whether they have been reconstructed correctly. Now, we need to measure the efficiency of the muon reconstruction. We can do that in the following way. You have a Z boson and it decays to 2 muons. We want to measure the probability that a muon candidate passes the muon reconstruction. What we do is we consider events with 2 muons, a Z boson, for example, and we tag one of those muons. In other words, we require that it satisfies tight reconstruction criteria. Now, the muon that we want to investigate, the probe muon, has a very loose definition. It could, for example, just be a track or a few hits in the pixel. And now we ask the question, what is the probability of a muon that satisfies the probe muon reconstruction to satisfy the full reconstruction chain? And note the idea here. The idea here is to gain information on to select a pure muon sample without running the reconstruction, and it is done by requiring that the 2 candidates, the tag and the probe, form a Z boson candidate. Okay, so we know, because we know the Z boson mass, we know the Z boson decays into a muon, and in a muon candidate, we tag one of these muons. And then we know enough that if we see a track candidate that has no muon properties, if these 2 guys, if this loosely reconstructed muon that has low quality forms the Z boson mass together with the other candidate, then we know for a fact that the second candidate is a true muon, irrespective of how we reconstruct it. And that's how we can select a set of muon candidates where we know those are muons without looking at the reconstruction. We just require that the mass forms together with the second muon, forms a Z boson. And once we have this set of candidate muons, we can look at their quantities and we can say, okay, I now run my muon reconstruction on these candidates, and I find that in 95% of the cases, I successfully do so. 5% of the cases are lost because of effects that are beyond my control. That means we have a 95% efficiency of the muon reconstruction, measured in data with measured in data, and that's a great achievement because how else would one select muons in a detector? Nobody tells you what's right and what's wrong. You have to take a look and you have to say, okay, if I have a good muon and if I have something that's very loosely reconstructed, but together these two things form a C boson candidate, then I know the second muon is in fact a true muon, and now I can run my reconstruction algorithm on it and test whether it is successful. So in this way, we can measure the probability of a probe muon to pass tight event selection thresholds. So we can measure with the tag and probe technique muon efficiency in data without any further assumptions. Something that I alluded to in the beginning, another concept is blinding. We shift gears again. The diagram to the right shows the measurements of the speed of light versus time and the corresponding uncertainties. And it is alarming. See the fluctuations of the speed of light from the measurements in the 1880s. 300, that's when the first measurements were starting to become accurate. You can look at the y-axis here. It does not have a larger spread, but still. So first measurement was close to 300,000 kilometers per second. Now, people were not at all concerned about statistics, systematical uncertainties, and the blinding process. So the first measurements all found with independent methods too high values. In hindsight, it was clear that the measurements were tuned as to not disagree too much with the famous professors who had done the measurements before, until suddenly one measurement found a much lower value with a new method with a much lower uncertainty. And then all the following people found that number, until somebody found, yet with a smaller uncertainty, an even lower number. And then all the people found that number, until somebody in the 50s found a slightly higher value, and then everybody found that value, and now we think it's correct. That's the problem of unblind. That's what happens if you look at the data and you change your measurement setup. You consciously or unconsciously affect the outcome. You tune your procedures, selections, setup such that it produces the least varying result. This is a historic example. We have many examples in high energy physics where the blinding policy is violated, and that's a sign of real danger. Then at this point, you start to harm the scientific process because you gather fake evidence. You gather evidence, you reduce uncertainties where you should not reduce them. Because whatever you're going to do, it will be combined with your predecessor and will be put more weight on a measurement that was wrong, and it will be more obscured. So somebody else will have to walk back all the way that you were going. So that's why unblinding is important, not only for searches, when you search for supersymmetry, when we always do it, but also for standard model measurements. Like the top mass is a good example. Top mass is not predicted by the standard model. It's very important to measure. We think we know it. We think it's 172.5, but it changed by 8 GeV, way outside the uncertainties since the discovery, way outside the uncertainty, because systematic effects were neglected. People did a good job, but not everything was always blind, and now we strictly blind the top mass measurements. So there are several strategies to deal with this. One can do a full blinding. One can just never look at the data. One can do a partial blinding. That's for analyses that are systematically limited. Well, you can actually, if they're systematically limited, you can partially unblind so that you are still statistically limited. Then you can carry out your analysis, even look at the signal region, even make tuning, because you're statistically limited. You will not bias your result, at least there's a large statistical component in the uncertainty that disguises any systematic tuning that you may undertake. And then you unblind once you've frozen. One can also bias the data with an unknown value. That's done in, for example, the G-2 Muon oscillation experiments. These experiments measure the oscillation of a muon as it oscillates, the spin oscillation of a muon in a magnetic field to measure the G-2. Those measurements have been already carried out with extreme precision by the G-2 experiment is at Fermilab. 7 teams work on the same measurement. They all work on the same data with different methods. And each data set is biased by a kept secret frequency. So they don't know what the other is measuring. Recently, they have been unblinded, but only with respect to each other. So it's now clear that everybody measures the same frequency, but it's not clear what that frequency is. Soon, hopefully, these measurements will be unblinded, and then we will have measured the G-2, the anomalous muon magnetic moment, which is one of the deviations in the standard model. In case you want to know more, just Google muon G-2 and start reading. There's great accounts of this in the science literature. Okay, that's what I wanted to say about blinding. Now let's look at the look-elsewhere effect. The look-elsewhere effect is the statistical effect of looking elsewhere, of conducting a search in many search bins simultaneously. In a search for new effects, one needs to take into account how many bins are considered. Look at the distribution below. I do not tell you what it is, except it is a mass. So it's the invariant mass of a system of particles. And this is very finely binned. So you get plenty of measurements with large uncertainties. And you can fit the background shape, that's the smooth function here. And now you ask yourself, is there a peak somewhere? A peak would be indicative of a new particle, okay? So here we have, let's say, order of 1,000 search bins. And now we make a fit for a peak. We do not know where the hypothetical particle may reside. It could have 30 GeV, like is shown here, or I don't know, 100. So we test the hypothesis of 30 or 40 or 50, and this is what we find. We find an excess around 30, and it's significant. Is several sigmas high. There's really a significant excess if you test the hypothesis of a particle with a mass of 30 GeV. However, you've searched in many bins. If you've searched in 1,000 bins, it's expected that at least one bin will have an excess that has a p-value of 1 in 1,000 or less. Okay? If you search 1,000 times, you find something unusual, something that happens with a probability of only 1 in 1,000. If you throw your dice 6 times, you can expect to throw a 6. If you throw a dice 10,000 times, you can expect to see something that happens only 1 in 10,000 times. That's the look-elsewhere effect. It always applies when we search for a particle whose mass we don't know. A good example is the discovery of the Higgs boson. We did not know a priori what the Higgs boson mass is. So we tested the Higgs boson standard model hypothesis as a function of its mass, and we looked at the different measurements. So here, Higgs decaying to photon, Higgs decaying to 2C bosons, WW, tau, tau, BB. These are all different analyses, different groups of people, mostly PhD students, who run this analysis and then who test the result against the data. And we find at the mass of 125 for this particular combination a p-value of 100 and less than 5 sigma, which amounts to discovery. Okay, but this has we have to take into account that we did not only search at 125, we search in the whole mass range. And by simulating what we do, trying the different mass hypotheses, trying this out in these various searches, amounts to a reduction of the global p-value with respect to the local p-value. The local p-value is the probability of the data to be as compatible with the standard model, as compatible with the Higgs mass hypothesis as is at a mass of 125 or more. And the global p-value takes into account that we've tested all the hypotheses. And in fact, for the result shown here, the global p-value that is from, I think, 2013 is only 4.5 sigma. So despite the fact that we can obtain a 5 sigma discovery threshold if we tested only the 125 GeV Higgs mass hypothesis, this is not yet a discovery, just because we've tested so many other channels, and it is not excluded to find fluctuations of this size in any of the bins if you search in enough of them. The quantitative problem is that you need to estimate the number of trials. Look at the diagram to the left. How many fits did you do? It depends on how wide this shape is. It depends on how many measurement bins you have, and it also depends on the detector resolution. If your detector resolution cannot discriminate 3 consecutive measurements here, then these are not significant and you haven't actually measured anything. So it's a bit of black magic to estimate the number of trials. Depends on detector resolution and signal assumptions. So that's important when we interpret the statistical significance of a measurement. We need to take into account how many times we tried. You probably haven't understood this. It took me, I remember when I, long time ago, first heard this. It's nicely illustrated in this XKCD sketch. Scientists are supposed to investigate whether jelly beans cause acne. Scientists find no link with a p-value or greater than 0.05. Then scientists are asked to go back and test different colors. They test 20 colors. Now you ask brown jelly, pink jelly, whatever. One of these really finds that there is a link between jelly beans and acne with a p-value that's smaller than that. And hence green jelly is linked to acne with green jelly beans are linked to acne with 95% confidence level. But because you tested 20 times and 20 times times 5% is 100%, is actually what you expect. That's an illustration of the look elsewhere effect. Okay, let's wrap up. We are at the end of the lecture. I again took longer than I thought, doesn't matter. We really have gone through a lot. We looked at these diagrams of the Higgs boson discovery in the beginning, and now you can answer plenty of questions, okay? Even though maybe you don't know yet, but you do know a lot about these measurements. You know which experiments these were taken from. We talked a lot about CMS and Atlas, which facility the results are from, in this case, the LHC, what collider that is, how the protons in that case are accelerated, are collided. You see, you can read off the data set. It was taken at 7 and 8 TeV proton-proton center of mass energy. You understand the luminosity. It's 5.1 inverse femtobarn. You know that the femtobarn is an area, it's a unit of cross-section, and that the luminosity is an inverse cross-section. And you know that you can multiply a cross-section with a luminosity to obtain a number of events. Today we've discussed that we have data points here whose uncertainty roughly is square root of n. We have a background estimation obtained in this case from simulation, a background subtraction, a signal hypothesis. This is Higgs going to Z bosons and 4 muons. We know when the protons collide that the parton model condenses our knowledge of the parton distribution functions, the quarks and the gluons in the proton. We know that we can compute the predictions in the by means of derivative matrix element calculations, but the things are more complicated because we have initial state radiation, we have hadronization, we have showering effects. And all these slightly obscure our analysis result. We have understood how the particles that are ejected from the high energetic collision travel through the detector in the magnetic field, that they radiate, that they interact with the different detector signals, that there are various concepts and technologies to record those signals. It is scintillation, ionization. There are various measurements being used, the EDX in the TPCs, the spectrometer measurements in the tracking, the recording of the showers in the calorimetry can be electromagnetic or sampling hadronic calorimetry. We understood that what subdetector can measure which quantity. We've understood what level today. We've gone through the level of particle identification that's possible and how the various subdetectors are combined to obtain a description of an event and how densely populated those events are. And we've also discussed how the subdetectors are assembled in experiments such that we can fully account for the high energy physics process. We've also gone through estimations of the backgrounds, at least in principle. I understand that all this is a little bit hard to understand when you only hear that in theory. It's best done in practice. So I can encourage you to consider pursuing experimental particle physics. It's really rewarding, and to do some of the things on your own. That's all I wanted to say in the whole lecture. I am done. I stopped the recording.